So let's talk about calorimetry. Calorimetry is the metry, that part of the name is measure, of calor. Calor is heat. So we're going to talk about the measuring of heat. Calorimetry is how we do this. So let's talk about heat for a minute. Heat is Q, and the main principle of calorimetry is that the heat lost by the first object is going to be equal to the heat gained by the other object, except for that one loses, one gains, so we have to put a negative on one side or the other. It doesn't really matter which side we put it on, but one thing loses heat, one thing gains heat, so everything is the same except for the sign. We could also say, since delta H is really just heat as long as we're at constant pressure, and most things are, that delta H is also Q. So we could say that Q equals delta H. So sometimes we set it up as Q1 equals Q2. We use this when just one substance is transferring heat to the other, and there's no really change or change of substance. We're not changing one substance into another. We're just transferring heat. Okay, so just transferring heat to the other. Okay, we use this when a reaction takes place. Okay, and the heat gained or lost by the reaction. Heat gained or lost by reaction is either taken from, which would be lost. Oops, not lots, lost. Or it was given to, which would be gained, right? By usually the solvent. I'm going to put little brackets around there because it's not always a solvent, but it usually is. Okay, so we're going to talk about these things. Now, if we're going to do the Q1 equals Q2 thing, or the Q on the other side, where somebody's just losing and gaining heat, we can say that Q is how much of that stuff we have, its mass, times how much the temperature changes, that would affect the heat, times something that we put in the middle called that's symbolized by a C, which is called the specific heat. Now, specific heat is a measure of how much energy it takes to change 1 gram of a material 1 degree Celsius. So if we have more than 1 gram, well, that's taken care of by the fact that we're multiplying by the mass. If we're changing it more than 1 degree, well, that's taken care of by the fact we're multiplying it by the delta T. So if one thing is gaining heat and the other thing is losing heat, like we have with negative Q1 equals Q2 up here at top, well, how about if we just substitute in the MC delta T for those? Does that make sense? The mass of the first object, mass 1, times the specific heat of that first object, times the delta T of that first object. In other words, how much we have of it, how much energy it takes to change its temperature, times how much the temperature changed for the first object. And that's going to equal the mass of the second object times its specific heat times its change in heat. Because that energy can't be just lost to the universe. It doesn't just blip out of existence. It's transferred from one thing to the other. So however much energy in the form of heat, this is Q1, right? that's lost by one has to be gained by the other, Q2. And, of course, we have to put that negative sign in to show that one is lost and one is gained. So let's do an example of this particular thing. I've already written out the problem. So this piece of aluminum, we have just a chunk of aluminum. I don't know whether it's a block or just a blob or whatever we have. This big piece of aluminum is at 85 degrees Celsius, 85.1 in fact. So we're going to dump it into some water. So we got some water here. We got a blob of aluminum. This is aluminum, this is water. The aluminum's hot, the water's not. And you know that if you put two things together, and one's hot and one's not, they're going to kind of come to an intermediate temperature. Now we want to put this into some kind of container that's insulated, right? Because that will keep the transfer of heat going to the outside air. We want just whatever heat that the aluminum loses, we want that heat to be gained by the water. So we might even put a little cover over the top of it to just keep it from losing or gaining heat to the air. Okay, so now let's figure out a couple of things. Delta T. Delta T is the change in temperature. The change in temperature for the aluminum is 23.0 is the final temperature, right? Minus 85.1 is its initial temperature. Degrees Celsius equals the temperature changed to negative 62.1 degrees Celsius. Now, why am I suddenly using Celsius when we had to use Kelvin for everything before? It's because delta T is what we're doing here. Wherever there's a delta T, the two temperature scales are the same. Let's draw a little thermometer off to the side here and just digress for a moment to this. If I have 1 degree Celsius, that's 274 Kelvin. If I have 2 degrees Celsius, that's 275 degrees, or just kelvins, sorry, not degrees. 3 degrees Celsius is 276 kelvins. So if I go from 1 to 3, I've changed 2 degrees. But if I go from 274 to 276, I've changed 2 kelvins. Hey, it's the same. As long as it's the change of temperature, then it doesn't matter whether we use Celsius or Kelvin, we'll get the exact same numbers. Okay, so back to our problem. Delta T for, look what I left out. I said for aluminum up there and I forgot to put it in. There we go. Now we're going to do the delta T for the water exactly the same way. What's the final temperature of the water? Why, it's 23.0 as well, because they equilibrate, right? They come to the same temperature. Minus 20.9 degrees Celsius, and this change in temperature is going to be 2.1 degrees Celsius. Now remember, when we subtract or add our sig figs, cut off at the decimal place wherever is the least number of decimal places. So we have to cut off at the 10th. So we've suddenly changed from 3 sig figs to 2. Oh my. Well, that's what happens when you subtract. Okay, so now we're just going to plug into this negative m, only now I'm going to put it as water times the C of water times the delta T of water equals the mass of the aluminum times the C of the aluminum times the delta T of the aluminum. So this whole side is Q for water, and this whole side is Q for aluminum, and since we put it in an insulating container, we can say Q for aluminum, this is Q for water, and we can say that we think that these things ought to equal each other, except for, of course, the sign is different. One's endothermic, gaining energy. One is exothermic, losing energy. So now all we got to do is pop our numbers in. So we have the negative that was just from the fact that they're opposite of each other in sign. Then we have 650 grams for water. I want to stop for 1 second and say, why 650 grams? When the problem said 650 milliliters. because of the density of water is 1 gram per milliliter, we can just substitute that really easily. You can do a little dimensional analysis if you want to prove to yourself that 650 milliliters would equal 650 grams, just for water, not for other things. And then we get the specific heat for water. It actually happens that water, it takes 4.184 joules to move 1 gram of water 1 degree Celsius. Where'd I get that? Specific heat you get off of the table on page, put that up here by this other thing, page 196, where we explained where specific heat is. So you look on page 196 in your textbook, page 196 in your textbook, and there's a little table that tells specific heats. Notice that if you're in a different state, in other words, solid, liquid, gas, you have a different specific heat. So every substance has 3 specific heats, one for when it's a solid, one for when it's a liquid, one for when it's a gas. We decided already that delta T for water was 2.1 degrees Celsius, and the mass of aluminum is what we're looking for, so we'll just write that down. The specific heat for aluminum off of that same table is 0.900 joules per gram degree C, and then the delta T for the aluminum is negative because it changed a different direction, didn't it? It went down in temperature, negative 62.1. So then if we do our arithmetic, pop that into the calculator, and out pops the answer of 102 grams. Now, since one of our numbers is only 2 sig figs, we're going to be stuck with only 2 sig figs. So in order to show that that's 2 sig figs, we're going to have to rewrite that as 1.0 times 10 to the second grams. That's the mass of aluminum. So basically 100 grams of aluminum with 650 grams of water. Notice that even though there's less aluminum, it went down much more drastically in temperature than the water did. There's more water, but also, besides that, water takes a lot more energy to move it 1 degree Celsius, which is an amazing thing about water. It has a huge specific heat compared to most substances on the earth. Take a look at that table and look at what most of the numbers are. Not much comes close to water at 4 joules per gram degree C, which is a very significant thing in terms of life on the earth and equilibrating temperatures. It really helps us to sustain life, that we have all these oceans that absorb a lot of energy before they change in temperature, so that mediates temperature changes on the earth. Just a little extra side note. Anyway, this is calorimetry. You get the heat that's lost by one thing equals the heat that's gained by the other. Change the sign of 1 and we're good to go.